Okay, the plan for today, we have kind of a motley assortment of things. We'll see how far we get through it. We're looking to finish up chapter 7, so finishing 7.4, solving rational equations, working through 7.5, solving some applications with rational equations, and then getting us started on chapter 8, roots and radicals. Also, the Unit 2 exam was last week. I updated the scores yesterday, so if you haven't seen your updated score, most folks got at least a couple points of partial credit, if not more. So check your exam score on WebAssign to see the updated score. And we have two quotes of the day today, both by philosopher David Hume. Well, one quote and one idea. So the quote is, "A wise man always apportions his belief to the evidence," or "a wise person always apportions their belief to the evidence." Um, so I think particularly, as we're looking at things like, for instance, applications and so on, we're looking at applying mathematical principles that are very abstract and kind of work in the mathematical world, and we're looking to overlay those principles on the real world and try to understand the real world a little bit better. Um, this thought process can help us to understand the real world better, but we can also, uh, I guess, kind of put a little too much of our own uh, biases and our own, preconceived notions into the modeling process. So we have to be a little bit careful not to do that. Um, we have to look at the evidence that's there, maybe a little bit more objectively. So if we're studying physics or chemistry or something like that, it's a little bit easier to objectively look at the evidence. If we're studying something like economics, it's a little more challenging, right? There are many different perspectives on the same evidence. Also an idea by David Hume, that's sometimes called Hume's guillotine, and sometimes referred to as the is-ought problem, that roughly speaking, science is very good at answering is questions. So, is this true about the world? Does, nature work this way or not? Or how can we model it? And ought statements kind of sit outside of science, right? These are kind of wisdom questions like, okay, we are able to do this thing now. Should we do it, right? It's not necessarily true that we should do something just because we are able to do it, just because we're technologically capable of doing it. So questions are uh, questions that sit maybe a layer of humanity above the is questions, our understanding of the natural world. You know, if we can bend the natural world to our will in some sense, um, how should we do that and to what ends? So the uh, getting answers to difficult scientific type questions or science questions doesn't, there's kind of a divide that doesn't give us an answer to what we should do immediately. Okay, so let's quickly jump back to 7.3, simplifying complex rational expressions. This will be also a nice little warm up for solving rational equations. And we left this as an exercise last time to complete. So if you've worked through it, you'll recognize this problem. But we're looking to simplify this complex rational expression with, it's a fraction with a rational expression in the numerator, 2 over r minus 9, and a rational expression in the denominator, 1 over r plus 9 plus 3 over r squared minus 81. And we saw that probably the best way to think about this is a ratio of two rational expressions like this. I haven't really done anything here, but I rewrote it in a way that's maybe a little more clear what's going on. I have this rational expression grouped together. I have this rational expression grouped together. And now that I explicitly see the grouping symbols, it's a little clearer what I want to do. I want to simplify this one. This one's actually already simplified, but if it wasn't simplified, I would want to simplify it as well. And then I want to take their quotient. So let's look at the denominator. 1 over r plus 9 plus 3 over r plus 9, r minus 9. I'm not going to go too slowly through this one. I'm going to go a little quickly because, again, it was an exercise from last time, so you should have worked through it and you should be a little familiar with it. I see that I have a factor of r plus 9 in both terms. Didn't leave myself quite enough room, but I need a factor of r minus 9 in my first term to get a common denominator. So I put it on top and on the bottom. And I end up with r minus 9 plus 3 over r plus 9, r minus 9. Or this gives me r minus 6 over r plus 9, r minus 9. Now that is my denominator. And my entire rational expression comes down as, again, 2 over r minus 9 for the numerator, divided by my now simpler rational expression, r minus 6 over r plus 9, r minus 9. Something that we see here is that this first rational expression has a restricted value. R cannot be 9. This second rational expression, looking at it by itself, has a restricted value. R cannot be 9 or negative 9. But also this overall quotient, because we're dividing by the second brackets, when that whole second brackets equals 0, we also have a problem. In other words, r also cannot be 6. We pick this up because if I put r equals 6 in the rational expression in the second brackets, I would get a value of 0 for the star rational expression, for the denominator rational expression, and I would be dividing by 0. I have something divided by 0, can't have that either. So these are my restricted values. A little easier to see what they are after we do all of our simplification and factoring and so on. We haven't divided anything out yet. That's quite important. We just kind of got a bit of simplification by combining these two rational expressions in the denominator together. Now we're going to go ahead and invert and multiply. So we're going to invert our second rational expression. And we're going to multiply. And we see we can divide on r minus 9. We get, let's write it as 2r plus 18 over r minus 6. And this is the best we can do. We don't want to get a little overzealous and try to do like, 3 or like divide out an r here or something. That doesn't work. This is a quotient. We can divide out common factors between the numerator and denominator. But if we have separate terms in the numerator and denominator, we can't divide things out between one term in the numerator and one term in the denominator, something like that. Like the 18 cannot divide by the 6 and make a 3. So this is the best we can do, and we're still subject to these restricted values. We do see the implied domain restriction, r can't be 6, still floating around, but we lost the r can't be plus or minus 9 restriction. Okay, any questions on that? All right, jumping down now to the next section, solving rational equations. I don't know why I've forgotten to do this on like every one of these problems, but I'm gonna just so that it's a little easier for you to see on if you're on a smaller screen, I'm gonna bump these equations down to another line because OneNote will make the text a little bigger that way. Okay, there we go. So particularly when we have complex rational expressions, I try to do that, but that'll make these even a little easier to see. All right, so here we're looking to solve rational equations, and the kind of main algebraic steps are we multiply to clear denominators, to clear fractions. We simplify everything, get everything onto one side, expand out, combine like terms, etc., and we solve. So we might end up with a linear equation to solve. We might end up with a quadratic equation to solve. We solve that algebraic equation. We do have an extra challenge here, an extra nuance in that when I multiply through to clear denominators, I'm not just multiplying through by a number, I'm multiplying through by something with a variable in it. And when I do that, similar to how up here, I kind of lost my clear domain restriction that R cannot be plus or minus 9, right? I didn't see that implied in the end result here. I had to lean on my previous explicit statement of the domain restriction. I could end up with an extraneous solution, as we might call it. So the first thing that we do is we're going to find all restricted values for all of the rational expressions. So in this case, we can see x can't be 7 or 4, or however this factors, it'll factor in x minus 7 times x minus 4. But so we find all restricted values. Then we go ahead and we do all of our standard algebraic steps. And then at the end, we want to take all of our potential solutions, the ones that we found from doing those algebraic steps. We want to check them against the restricted values. If we have any restricted values, we just get rid of those. Those are no longer candidates for solutions. And then we always should check our remaining solutions just to make sure that they do result in a correct equation. So first, our restricted values, we do see that the first rational expression's denominator will factor into x minus 7 times x minus 4. So x cannot be 4 or 7. Now, from this point until the end, I'm going to basically forget about these restricted values and just work with this algebraically. So I'm going to multiply by x minus 7 times x minus 4. This denominator is x minus 7 times x minus 4. When I multiply through, I just get x plus 8 on the left-hand side. On the right-hand side, I have to distribute x minus 7 times x minus 4 to both terms. In the 5 over x minus 7, the x minus 7's divide out. I'm left with 5 times x minus 4. And on the right, the 2 over x minus 4, the x minus 4's divide out. I'm left with 2 times x minus 7. I have a linear equation, one variable. This is easy enough to solve. I distribute, combine like terms, get my variable terms on one side, isolate my variable terms, and isolate my variable. So I have 5x plus 2x gives me 7x. Minus 20 minus 14 is minus 34. I'll get my x's on the right side, which gives me 6x. And then I can add 34 to both sides, give me 42. And then, of course, I get x equals 7 as something like a candidate solution. So what I mean here, I guess this is steps 2 through 4. So what I mean by a candidate solution is if there is a solution to this rational equation, then it must be 7. That if then though only goes one direction, not saying that if x equals 7, then it is definitely a solution to the rational equation. I'm saying that, let's find all potential solutions. Nothing other than x equals 7 can be a solution. is x equals 7 allowed to be a solution? Well, we actually note that x equals 7 is a restricted value. If I were to try to plug it in and see if I get something that makes sense, I get 5 over 0 plus something equals what's 15 over 0, right? How does 15 over 0 equal 5 over 0 plus 2 over 3? I mean, 15 over 0 and 5 over 0 are undefined. Uh, so that's just like, that's not a sensible mathematical claim to make. The only candidate solution we had was x equals 7. We remove it from the pool of candidate solutions because 7 is a restricted value. And because, of course, even if we forgot to check for restricted values, if we went to plug back in the check, we would see that pretty clearly something has gone wrong here. So there are no solutions. So we have no solutions to this rational equation. Any questions on any of this? Okay, next example. Let's solve this rational equation. X over x plus 7 minus 8 equals 98 over x squared minus 49. So again, step 1, let's find restricted values. X cannot be plus or minus 7. We see that that x squared minus 49 is going to factor into x plus 7 times x minus 7. And we see the other denominator of x plus 7. So these are our only restricted values, plus or minus 7. Now we'll solve algebraically. Again, I know x squared minus 49 turns into x plus 7 times x minus 7. I'll multiply through by that. Maybe a little bit more careful this time because we have a little bit more going on here. On the left side, x plus 7, x minus 7 multiplies onto x over x plus 7, as well as the minus 8 term. And on the right side, I have what amounts to 98 over x plus 7, x minus 7 times x plus 7, x minus 7, or just 98. I see my x plus 7s divide out over here. I'm left with x squared minus 7x. And then I have minus 8 times x squared minus 7x plus 7x is, that goes away. And then minus 49 equals 98. I have x squared minus 7x minus 8x squared. And I have plus, well, 8 times 50 would be 400. I don't know why I had a mental whatever lapse there. So 8 times 50 will be 400. So 8 times 49 is 400 minus 8, or 392 equals 98. And x squared minus 8x squared is negative 7x squared minus 7x. And then 392 minus 98 is plus, that would be 296, right? So 98 is 92 plus 6. So if I subtract 98 from 392, I get rid of the 92, and then I have, oh, glad that I checked. 294. 92 is 90, or 98 is 92 plus 6. So if I subtract 98, I've got to get rid of the 92 and then get rid of another 6. 300 minus 6 is 294, not 296. And then, okay, so 294, it would be nice if there was a factor of 7 in there. I wonder if there is. I know that 7 times 30 is 210, and then that would mean 84 left over. And 84 does have a factor of 7 in it. So let's see, 294 over 7. 7 goes into 29 4 times. 4 times 28. 7 goes into 14 2 times. 2 times 7 is 14. Remainder 0. So we can divide through by 7. Let's divide through by -7. So you get x squared plus x minus 42 equals 0. Okay, I'm looking for two numbers that multiply to -42, so opposite signs, and that add to +1. So the bigger number should be the positive one. I think that is 7 and 6. So x plus 7, x minus 6, so that they are opposite signs and the bigger one gets the positive. Or x equals +6 or -7. Again, these are candidate solutions. If there is a solution to this rational expression, it has to be in this list. No number that's not in this list, -5 or +12, is going to be a solution to the rational equation up there. These are candidate solutions, but again, I recognize that -7 is a restricted value. I remove it from consideration. +6 is not a restricted value. So what do we do with it? Well, let's check it. I'm going to copy this down. We're going to check it all the way back in the original rational equation, not in some simplified form, but in the original one. So let's check x equals 6. Or that's 6 over 13 minus 8 times 13 over 13. Is that equal to 98 over 36 minus 49? So that would be -13, right? I can get rid of all my 13s. Is it true that 6 minus 8 times 13, is that equal to -98? So what is 13 times 8? Looks like 104. Is it true that we can flip the order? 104 minus 6 equals, flip the order by multiplying by -1, 98, and that looks good. So x equals 6 is our verified solution. X equals -7 is not a solution. It was a restricted value. So we have exactly one solution to this rational equation. That is x equals 6. And if we had mistakenly forgot to check for restricted values, or if we thought x equals -7 was a solution, we would have plugged in and we would have pretty quickly seen that we got something over 0 on the left and something over 0 on the right. And that would have clued us in that somewhere something went wrong. Okay, and then last question in this section. What about solving a rational equation with two variables for one of the variables? So solve 1 over p plus 2 over q equals 4 for the variable p. So in other words, I want to do some stuff and get p equals blank. Well, this isn't too hard to solve. We can use similar steps to how we solve these up here. We can clear fractions, do our algebraic solution methods, and then get an answer. I know that P can't be 0, so I probably should just write that out just to be clear. We're thinking of P as the variable here. So let's multiply through by P. And now really what I have is a linear equation in P. If I write it this way, it might be a little clearer. 1 plus 2 over Q times P equals 4P. I have number plus coefficient. Well, we're thinking of Q basically as a number. 1 plus number times P equals number times P. I can subtract 2 over QP to the other side. And then I can divide by this new coefficient. And that's what P would be in terms of Q. I see it in this particular problem, I could have gotten here a little more quickly by taking a little shortcut. I could have noticed that I can get 1 over P by itself really easily. And then I can just invert both sides. I can basically like cross multiply or cross divide or something like that. I can just say that P is then 1 over 4 minus 2 over Q and get the same answer. So in this particular problem, there was a quicker way to solve it, or we could go through our equation solving steps and still get the solution, no problem. In a more complicated problem, you might be more constrained to go through all of these steps. Any questions so far? Okay. So let's look at a few applications with rational equations. We're going to start off with a pretty straightforward one. So a veterinarian prescribes Sunny, a 63-pound dog, and an antibacterial medicine in case an infection emerges after her teeth were cleaned. If the dosage is 5 milligrams for every pound, how much medicine in milligrams was Sunny given? I actually just had to do this. It's kind of a long story, but my wife and I have a dog, and he takes some medicine with each meal. It's like a little powder that we sprinkle on his food, keeps his GI system happy. And we just put in an order for it, and the vet said, yeah, I'm happy to approve the order. We put it on Chewy, and they have to get the vet's approval. So I'm happy to put in an order, but what is the dosage? And we're like, well, it's a pinch on his food. That's literally what the prescription says. It was from another vet. So I went back and figured out, okay, this bottle has, how many grams of active ingredient, over how many meals, when was the last time that we had ordered it, figuring out how many milligrams per dose we ended up giving him. So this is actually a pretty similar problem. So I literally just did this yesterday to send to the vet and say, this is about the dose we're giving him. Is that in line with, what you're happy with? So, okay, so there's a couple of ways to do this, I suppose. I think that the nursing folks like using the dimensional analysis, as it's sometimes called. So what am I looking for? I want to know how much medicine in milligrams was Sunny given. So that's my variable. My other dimension, my other unit is pounds. So I want to set up an equation where I have milligrams per pound on one side and milligrams per pound on the other side. If I think of my units and get my unit straight first, then that helps me not to get things flip-flopped on one side or the other, right? I know that the dosage given is 5 milligrams per pound. I know that Sunny weighs 63 pounds. So again, I might be tempted to do something like 63 over X. But I know that will be wrong because I know that the pounds should be on the bottom. And then what I'm looking for is what is the dosage, how much medicine, X milligrams. Now I see that my units are all going to go away. I could basically multiply through by pounds per milligram and get rid of my units on either side. And I have X over 63 equals 5 over 1, or just X equals 5 times 63. So what is that? 315. So we should give the dog 315 milligrams of, of the medicine. Now, if I had set this up as pounds per milligram instead, well, then I'd have gotten a harder equation to solve, but it still would have worked. 1 pound per 5 milligrams is 63 pounds per X milligrams. And then I'd have got 63 over X equals 1/5. I can clear fractions, basically just cross multiply. X equals 5 times 63, 315. I'd get the same answer if I set it up the other way. But, using a little bit of foresight, I realized that this might be an easier way to set it up. But now that I have a strategy for solving rational equations, I know that this will work just as well. Okay, let's take a look at this example. So Mike, an experienced bricklayer, can build a wall in 3 hours, while his son, who is learning, can do the job in 6 hours. How long in hours and minutes does it take them to build a wall together? Something like this can be a little bit challenging to work through. So let's use the strategy your book uses and kind of write out a grid. So we'll look at 3 scenarios: if Mike was doing it alone, if his son was doing it alone, and if they were doing it together. The number of hours to complete the job with Mike doing it alone would be 3 hours. The number with his son doing it alone would be 6 hours. And the time that it takes them to build it together, let's just give that a variable. We'll call it T. We don't know what that is yet. Now, we certainly don't have something like 3 plus 6 equals T, right? That's not what we have. T isn't going to be 9 hours. It's not going to, them working together isn't going to make it take longer than if they were working separately. So what we want to do is look at the proportion of the job completed per hour. Per hour. Well, Mike completed the whole job in 3 hours, so the proportion completed per hour is 1/3. The son, 6 hours, so the proportion completed per hour is 1/6, and together T, the proportion completed per hour is 1 over T. So each hour, they chip away. Mike chips away at 1/3 of the job, the son chips away at 1/6 of the job, and that does equal 1 over T. So we do have 1/3 plus 1/6 equals 1 over T. 1/3 plus 1/6 is 1/2. Or T equals 2 hours. So it'll take them 2 hours to complete. Does that make sense? Yeah, it does. It should take them less than 3 hours, because if Mike was doing it alone, it would take him 3 hours. His son's helping, it should take less than 3 hours. But it shouldn't take 1.5 hours. It should take more than 1.5 hours, right? Because it would, like if I had 2 Mikes, if I had 2 experienced bricklayers, then either one of them could complete it individually in 3 hours. Both working together should complete it in 1.5. So I know my answer should be longer than 1.5 hours because the sun isn't quite as quick as the experienced bricklayer, and should be less than 3 hours. And uh, that is what I see with my answer, between 1.5 and 3, as I expect. Now, one aside here, I think this is just this isn't, so much a math idea, but really a modeling idea. We're trying to take these abstract models and overlay them onto real world problems. These types of problems assume 100% parallelizability. And not all problems can be completed in parallel, right? So, if you think of like the famous Lucy and Ethel, scene from I Love Lucy, where they're stuffing the chocolates into wrappers, like that's pretty parallel. If you have, 5 people working on a line, as long as the candies are coming out fast enough, they're going to stuff 5 times as many candies into wrappers as if you had one person on that line. And that's because each person takes one candy, puts it in their wrapper, sticks it in the candy box or whatever, and that's their job. But not all jobs work this way. For instance, if you look at roofers, or what if, say, one roofer can lay 100 square feet of shingles an hour, how long would it take 3 roofers to lay shingles on a 600 square foot roof? We might say, okay, if we had 2 hours, each roofer is going to lay 200 square feet of shingles. That makes 600 square feet. But the real answer is probably a bit longer than 2 hours, probably a non-trivial amount longer than 2 hours. I mean, unless it's an enormous roof and one of them's working way over here and one of them's working in the middle and one of them's working way over on that side, at some point their shingles have to overlap, right? They have to start interacting with one another, or they get to the top and somebody's got to put the cap shingles on. So in reality, there's a little bit of communication that has to happen there. There's a little bit of kind of interaction effect. Or if we look at, say, a relay race, if a sprinter can run 400 meters in 60 seconds, how long would it take 4 sprinters to run a 400-meter relay? Well, number one, it's not going to be 15 seconds, because if it's a relay, it's not like they can't all start at the same time, right? Each one has to wait for their job, for the previous person's job to be completed before they can start their job. It's almost like an assembly line, right? If I'm the person on a car assembly line that puts on the doors, well, the person that puts in the dashboard has to finish their job completely before I can put on the doors. I can't be putting on the doors while they're trying to still put in the dashboard, right? So this is something that's really not parallelizable. So it'd probably take around 60 seconds, right? Or kind of a silly answer, but this is one of those types of answers that you'll see somebody will ask like ChatGPT a question like this, and it'll come up with an absurd answer, because it kind of sounds like one of these types of questions. But, a normal person would recognize right away that this is a silly question. If one violinist can play Mozart's 40th in 25 minutes, how long would it take an ensemble of 5 violinists to play the piece? It's not going to take them 5 minutes, right? I mean, it's still going to take 25 minutes. It's not like violinist 1 is going to play the first fifth and violinist 2 is going to play the second fifth at the same time, and right. So we do have to keep in the back of our mind that if we're applying this to real life, there are scenarios where this doesn't apply at all, something like this. There are scenarios where the interaction effect is huge, where person 2 has to completely wait for person 1 to finish their task before taking the baton and running with it. Like, say, an assembly line for, say, a car or something like that. It's hard to have more than one person working on that car at the same time. And there are places where the interaction effect maybe is non-trivial, but isn't such a huge deal, right? The roofer or even the bricklayers, right? I mean, if the 2 guys are building a wall, like, how are the 2 of them working together? If it's like Mike places 1 brick, then his son places 1 brick, then Mike, then his son, it's probably gonna take them longer than 3 hours to do that, right? Like, just the coordination is going to get so much in the way, they're going to be tripping over themselves. This also happens with computers, by the way. It's a really important idea today that computers can do parallel processing. They can take a big task, break it into smaller tasks, and run each of those smaller tasks maybe on a different processor or a different core of a processor, something like that. And you don't get, it's not linear in the number of processors that you have, the amount of work you can do, because there are interaction effects. Some problems are very parallelizable where it's almost linear. Some problems are really not parallelizable at all. Like if I'm trying to evolve a physical system over time, I kind of have to solve the system at time 0 before I can take a time step forward. I can't guess at what time step 10 is going to look like before I computed time steps 0 through 9. So just kind of an aside on that. So implicitly, we're assuming in all of these kinds of problems, for the sake of our text, that it's completely parallelizable, that there are no interaction effects between the two bricklayers or having to marry their work together or something like that, that they're working in a way that's completely parallel. But that's not always the case. Okay, and then last couple examples here. The length that a spring stretches varies directly with the weight placed at the end of the spring. So that's Hooke's law, if you remember that from science class. When Sarah placed a 10-pound watermelon on a hanging scale, the spring stretched 5 inches. So here we have direct variation. So we're looking for an equation that relates the length of the spring, or the amount that it's stretched, to the weight in pounds. So I copied this off of the book. When it says the length of the spring, really what it means is length past equilibrium. So the amount of stretch. Of the spring. Right, the spring is going to start with the natural length, but when we say the length of the spring, it means the amount of stretch of the spring. So varies directly means L equals Kp, means that the length of the spring is proportional to the number of pounds, the weight that is hung from it. I don't know what K is, but I can use this piece of information up here to find K. I know that a 10-pound watermelon, so when P is 10, stretches the ring 5 inches, gave me a length of 5. I can use that piece of information to fit my model to this particular system to figure out the value of my parameter. So L equals 1/2 P, or L equals P over 2, is the relevant equation for this particular spring in this particular circumstance. And then our question, what weight of watermelon would stretch the spring 8 inches? So if I want 8 inches, I need a 16-pound watermelon. Any questions on that one? Okay, so next example is a little bit similar. The pitch of a musical tone varies inversely as its wavelength. So it's similar in that we're going to construct a model and then use the model, but the type of variation is different, varies inversely. So suppose we have pitch, or frequency, we'll call it. So pitch versus L for wavelength. So suppose that one tone has a pitch of 440 vibrations per second, and that corresponds to a wavelength of 2.6 feet. If I say that pitch varies inversely as wavelength, I have F equals K over L. As a little aside, notice that if f equals k over L, I can multiply by L and divide by F. L equals k over F as well. So this inverse relationship, it kind of is the same relationship both ways. So this is my model. I have a piece of data for a frequency of 440 that corresponds to a wavelength of 2.6 feet. Or that tells me that 440 equals k over 2.6, or that k for this system is 440 times 2.6. So the model that fits this particular system, this particular musical instrument, whatever it may be, is F equals 440 times 2.6 over L. And then I want to use this. I want to find the wavelength for a pitch of 220. So I have 220 equals 440 times 2.6 over L. I have a rational equation to solve here. It's a pretty simple one, though. Clearly, L can't be 0, and clearly L is not going to be 0, so we don't have to worry too much about the technicalities. We multiply through by L, divide by 220. And so we see L would be 5.2 feet. So if we double the wavelength, we have the pitch. Okay, so any questions on anything we've discussed so far? Any questions on anything in chapter 7 with rational expressions, operations on them, simplifying them, solving rational equations, applications of rational expressions and rational equations, any of that? Okay, then let's start into chapter 8, roots and radicals, starting with 8.1, simplifying expressions with roots. Okay, so let's recall really quickly here the order of operations. We have parentheses first. Exponents and roots come next. Well, really, roots are exponents, right? The square root of 4 or something like that. We'll see fairly shortly here that we can write this as 4 to the 1/2 power. So really, a root acts like an exponent. Multiplication, division, addition, and subtraction. So when we think of exponents or roots coordinating with multiplication or division, they coordinate pretty nicely. They distribute pretty nicely. We have a distributive law that brings us one layer down on the order of operations, right? Multiplication, division can distribute into addition, subtraction. Roots can distribute into products or quotients, right? So if I have a times b to the n power, that's a to the n times b to the n. Or if I have a over b to the n power, that's a to the n over b to the n. Again, roots work like exponents. So if I have, say, square root of a times b, here we'll take a to be bigger than 0 and b to be bigger than 0. So square root of a times b is square root of a times square root of b. Or square root of a over b, same conditions, a and b both positive. That's root a over root b. So I could approach this two different ways. Square root of 25 over 64, I could look at as square root of 5 squared over 8 squared, or the square root of 5/8 all squared, basically using this formula with n equals 2 going from the right to the left. And if I have the square root of a perfect square, that's going to be 5/8. Or I could use a root property. I can make it square root of 25 over square root of 64 using this formula. Square root of 25 is 5, square root of 64 is 8. I can kind of square root the numerator and denominator separately, or I could square root the entire fraction. Either way, I get the answer of 5/8. If I look at, say, negative square root of 0.01, and decimals are a little bit, a little bit difficult to work with here. But I do notice that this is negative the square root of, well, that's 1/100th. Now, negative a square root, what exactly do we mean by that? I see that this is going to be negative 1/10. But if I had, say, square root of negative 0.01, is that equal to 1/10? Or is that equal to negative 1/10? Well, recall with square roots, saying that um, saying that 5/8 is the square root of 25 over 64, what that means is that 5/8 squared equals 25 over 64. And that is true. So if I were to try to do something like the square root of negative 0.01 or square root of negative 1 over 100, maybe I think this is like, I don't know, negative 1/10. But does that imply that negative 1/10 squared equals negative 1 over 100? Well, no, because negative 1/10 squared is going to be a positive number. This gives me positive 1 over 100. Is that equal to negative 1 over 100? No. So we have a couple ideas going on here. This is a bit of review, so I'm not handling this super formally, but we have a couple ideas going on here. So the first is that if, let me use two different letters instead of A and B. I've already used those. My OneNote is freezing up a little bit here. Sorry about that. There we go. Let's use M and N. If M equals N squared, then we say that N is a square root of M. In other words, 25 equals 5 squared. So 5 is a square root of 25. But 25 also equals negative 5 squared. So negative 5 is also a square root of 25. So 25 has two square roots, positive 5 and negative 5. The symbol that looks like this, the radical sign 25, this indicates the so-called principal square root. Of 25. That is the square root that is a positive number. So square root of 25, we wouldn't write it as plus or minus 5 like that. Square root of 25 written as radical 25 is 5. But 25 has two square roots, plus or minus 5. Or in fact, 25 has two square roots, plus or minus square root of 25. On the other hand, if m equals n squared, then n is the square root of m. What numbers can we square root? We cannot square root negative numbers, at least not yet, at least not in the real numbers. Right? I noticed that if m equals n squared and if m equals n squared and if n is a real number, then m has to be bigger than or equal to 0. So at this point anyway, the only numbers I can square root are non-negative numbers. I can talk about the negative square root of a positive number, right? Negative square root of 1/100th is negative 110. That negative is outside the square root. I cannot, well, at least at this point, talk about the square root of a negative number because I don't know what real number I should multiply by itself to end up with a negative result. Because if I multiply a negative number by itself, it's going to be positive. If I multiply a positive number by itself, it's going to be positive. If I multiply 0 by itself, it's 0. I can't multiply a real number by itself and get a negative output. So I cannot square root negative numbers, at least not yet. We will be looking at that fairly shortly, but as of right now, I cannot square root negative numbers, but I can talk about negative square roots of numbers. So if the negative is inside the square root, that's no good. If it's outside the square root, that's perfectly fine. That's just the opposite of whatever number I got from taking the square root. And I think that's probably a good place to stop for today. So we got a little bit of a start in chapter 8. When we come back, we'll just continue working through 8.1, 8.2, and continue through chapter 8. So let me stop the recording.